Today we will be discussing about chapter 3 of thermal. Today we will be discussing about chapter 3 of thermal engineering, which is laws of thermodynamics, and this is the first class in this chapter. So in this class we will cover what is heat, what is temperature, and basics about thermal equilibrium, and also we will see Zeroth law of thermodynamics, heat and work. We have already discussed about heat and work in the last class, and we will get deep into it, and we will learn about the sign convention of the heat and also work, how to derive work for a process, and also we will apply the first law of thermodynamics for a closed system when it is running in a cycle, or for a single process, which is non-flow process. There will be no flow, means it is a closed system. We'll cover these topics in today's class. So first we'll learn about heat. Okay, heat is one form of energy, but which will be flowing due to temperature difference mainly. If there is temperature difference, heat will flow from one place to another place. If we apply, we want to discuss about a system, say this is a system, and this is the boundary, and outside the system there will be surroundings. So say if the system temperature is 100 degrees centigrade and outside temperature is say 30 degrees centigrade, what will happen? Energy will start flowing from system to the surroundings. So this energy transfer is due to temperature difference, and that is heat. Okay, it is basically energy transfer due to temperature difference, and heat is a one form of energy in transit. Transit means when it is transferring from one place to another place. So coming to temperature, so temperature is basically degree of hotness or coldness. So in some cases we'll tell the temperature to tell how hot it is or also how cold it is. Say suppose if you say the temperature is 100 degrees centigrade, we can say that this is hot, or else if it is minus 10 degrees centigrade, you can say the body is cold. So to describe the state of the system, we'll use temperature. So here we have to understand the difference between temperature and heat. The main difference here is, so temperature is a property or state function. State function means say let us assume a PV diagram. Here the system is at this point 1. So at this point we can measure the temperature and say this temperature is T1, whereas we cannot measure heat because it has not undergone any process. So if this system follows a path and changes its state to 2, okay, by assuming this path we can calculate the heat. That is why heat is a path function, whereas temperature is a state function or point function. Okay, these heat and temperature are closely related, but yet they are very different from each other. So that is the main difference between heat and temperature. So coming to the thermal equilibrium, so thermal equilibrium is a condition where there will be no heat transfer. Okay, heat will not transfer from this place to one place to another place. When that will happen, say suppose there are two bodies, one is at say 55 degrees centigrade and another body is at say 30 degrees centigrade. So these two bodies are close in contact with each. So due to higher temperature of this body, energy will flow from here to here. I mean heat will flow from hot temperature body to cold temperature body. After some time what will happen? These two will come into thermal equilibrium. That means these two will be at same temperature, say 45 degrees centigrade and 45 degrees. At this point there will be no heat transfer. That means these two are in thermal equilibrium. When the temperatures are same or there is no heat transfer between two bodies, then we can say that those two bodies are in thermal equilibrium. Okay, basing on these three, we will define what is zeroth law thermodynamics. Okay, so this is zeroth law, that means zero. Why this name came like this? So initially after finding some studies, they have discovered first law of thermodynamics and second law. Later they came to know that there is one more law of thermodynamics which is very basic. So it cannot be third law because it is not that much complicated. So they have put it zero, said this is zeroth law of thermodynamics. Okay, so in zeroth law of thermodynamics, say suppose there are three bodies, A, B and C. Okay, so here what the statement of zeroth law of thermodynamics is, if there is a body A which is in thermal equilibrium with body B and also in A is in thermal equilibrium with body C, then we can say that these two are in thermal equilibrium. Simply mathematically it says if TA is equal to TB and TA is equal to TC, then we can say that TB is equal to TC. If a body is in thermal equilibrium with two bodies, separately, then those two bodies are also in thermal equilibrium. That is what zeroth law of thermodynamics states that. Okay, so this is basically what we are saying is this. That is why it is very basic and is named as zeroth law of thermodynamics. Okay, next we'll see heat and sign conventions. Heat and sign convention. So already we have discussed about heat. Heat is, say there is a system and this is the boundary. And outside the system there are whatever outside whatever may be there, that is called as surroundings. So whenever there is a temperature difference, energy will cross the boundary and go to the surroundings. So this energy transfer due to temperature difference is called heat. Okay, and also in some cases this temperature may be less and outside temperature may be high, then heat will transfer in this direction. That means here it is called as heat is supplied to the system. Supplied to the system. Here it is called as heat is rejected by the system. That means heat is going out of the system. So there are two cases of heat. So whenever heat is supplied to the system, this is taken as positive. Whenever heat is rejected by the system, it is taken as negative. So Q is, that is heat is positive when heat is supplied. Heat is supplied to the system. Q is positive. Q is negative when heat is rejected. It is rejected. So you can assume like this. Say suppose there is an engine. There is an engine. So suppose this is a engine. What is the purpose of engine? Engine has to take thermal energy, that means heat energy, and converted into mechanical energy, which is this is work, this is heat. An engine has to convert heat into work. So that is easy. Our aim of this subject is to study this, to convert heat into work. That is why whenever heat is supplied to the system, it is taken as positive. This is the desired effect by us. And this is the, whenever heat is going out of the system means we are losing the heat, that is negative. That is why heat supplied to the system is taken as positive. Heat rejected by the system is taken as negative. And also say there is a process PV from here to here. Okay, so Q1 to 2, it is written as 1 to 2. Q means heat transferred, and 1 to 2 is from process 1 to 2 equal to integral dq. That means small amount of, say suppose here this is the small amount of heat dq. So total amount will be integral of dq. So integration is from 1 to 2. This is the formula for heat transfer, and these are the sign conventions. Whenever heat is supplied, it is positive. Whenever heat is rejected, it is negative. Next we will see what is work, expression to calculate work, and its sign convention. So work is also a energy in transit. It is also measured whenever energy is flowing across the boundary. So here this energy is mechanical energy, and this is done, this difference in energy is occurred due to force or pressure difference. We will see how. Say there is a piston and cylinder arrangement, okay, like this. So here inside there is a gas, at certain pressure P1. Then outside the, say suppose there is a pressure of P2 outside the system. This is the system, this is the boundary, and this is our surroundings. So if P2 is greater than P1, what happens? So here pressure is more, so it will the piston will try to compress the gas inside the system. That means there is force and it is getting displaced by this much. Say if P1 is greater than P2, what happens? This gas will try to push the cylinder and piston will move in this direction. So let us assume P1 is greater than P2. So this is pushing it. So this piston will be pushed by this gas until P1 equal to P2. Whenever the gas pressure is equal to the outside atmospheric pressure, this motion will stop. So say this is the distance moved by piston. So work is equal to force into distance. This derivation we have done many times. Force into distance or displacement. So force can be written as pressure into area multiplied by ds. So this can be written as PdV. Area into displacement is volume, that is change in volume. Here pressure is not constant. Initially it is P1 and finally whenever the piston reached the end of the movement, the pressure becomes P2. That is why whenever we have to calculate W1 to 2, that means say this is the PV diagram. Initially the pressure is more and volume is less. This is P1, this is P1. So this is expanded like this. This is V2, this is P2. So if you take a strip of this area, this is pressure P and dV. Area under the curve is P into dV. If you integrate from 1 to 2, you will get the work from the process 1 to 2. This is the formula for any process. For any process, this formula is common, and from this formula we will calculate the work depending on the pressure. So here, as I said earlier, what is the purpose of engine? Engine has to take heat and it should produce work. So here work done by the system is by the system. That means whatever the work is coming out of the system is positive, because our aim is to get work from heat. So work done on the system is negative. Okay, say if the work is going inside the system, then it is negative. If it is coming out of the system, it is positive. Heat is, whenever it is going into the system, it is positive, and whenever it is coming out of the system, it is negative. We have to remember these 4 sign conventions. Okay, it is very important. Heat is to be supplied to the system and work we will get from the system. So now we will see how work transfers from the system. We can say that if there is another form of transfer is this. Say suppose there is a system, this is the system, this is the boundary, these are surroundings. There is a paddle connected to this. Paddle means a stirrer like thing. So this is the stirrer. So I am doing like this. A thread is bound around the shaft and a weight is being hanged. So if you release this weight, what happens? This shaft will rotate, and this work, whatever the work is done, it is transferred to the system. So work is coming into the system, that is why this is negative. So work is transferring from outside the system to inside the system. Say if you assume this shaft and this weight as a system, say this dotted line is now my system. This is the system, this is the boundary, and everything external to the system is surrounding. So here what happens? The work is transferred getting out of the system. So this is positive work for this system, whereas it is negative work for this system. Okay, this is how work may be transferred. If it is a shaft, it will be transferred like this. If it is a piston and cylinder, the transfers will be like this. The transfers will be like, okay, this is how work and heat are described. So now we'll see what is first law of thermodynamics. Okay, so first law of thermodynamics is basically, this is also known as energy conservation principle. Okay, energy conservation principle. A simple statement for this is energy can neither be created nor be destroyed. But can be transferred from one form to another form. This is the energy conservation principle which we have studied in school and physics. Whereas in thermodynamics, it can be rewritten as like this: heat and work. These two are the main properties which we are studying this thermodynamics. Heat and work are mutually convertible. Mutually convertible means heat can be converted into work and work can be converted into heat. If you have any doubt that work cannot be converted into heat, say suppose there is a rough surface and another block which is having rough contact. So this is having some weight, and if you move this work by some distance, we are doing this amount of work, weight into distance. So what happens is, whatever the work is done, due to this friction, it is getting converted to heat. So here work is converted to heat. Okay, this way work can also be converted to heat. Another example is rubbing of hands. So in winter we will rub our hands to get heat. Similarly, here also work can be converted to, these two can be converted each other, but we cannot create work out of this. Say suppose if you have 100 joules of heat, this can be converted into only 100 joules of work, not more than that. Okay, similarly vice versa, only the same amount can be converted. You cannot create extra work or extra heat from this. That is what first law of thermodynamics is telling us. And here in SI units we use both joules, whereas in MKS units heat units are calories, and whereas work units are joules. So work units are joules. So we know that 1 calorie is equal to 4.187 joules. So in olden days, this integration of Q is equal to integration of work, but it should be multiplied with J. This is called as mechanical equivalent of heat. This is called as mechanical equivalent of heat, which is equal to 4.187. Okay, or J is equal to integral W by integral Q. So in SI units both are calculated in joule, so J is equal to 1 in SI units, whereas in MKS units it is equal to 4.187 joules. This is first law of thermodynamics basis. Now we will see how to apply for a cyclic process. Cyclic process means we already know that what is a cycle. Cycle is we can say that a system has undergone a cycle when initial state and final state are same. So there is a one process from here to here, 1 to 2, and another process from 2 to 3, and finally it has come back to 3. So this is the process. Okay, so we can say that 1, 2 to 3 equal to a cycle or cyclic process. Cyclic process. So during this cycle, say suppose during 1 to 2 process there is expansion, so there is work output and heat input. Okay, there is work output and heat input. So this is Q1 and this is W1. And during 2 to 3 process it is constant volume process, there is no work, only heat is rejected. Okay, and during 3 to 1 process again there will be some it is compression process, so it is W3 and there is some heat rejection Q3. So first law states that heat and work are mutually convertible, and also these two are equal. Okay, so here there comes cyclic integral of Q and cyclic integral of work, but that means we have to sum all the heat inputs and outputs of this whole cycle, and also work input and outputs of the whole cycle. Then you can say that here same. So get into details. Here Q1, Q2 and Q3, there are 3 Qs. So Q1 is heat supplied to the system, so it is positive. Q2 is heat rejected by the system, that is negative, and Q3 is also it reject coming out of the system, so it is also negative. Whereas work, there is W1 getting out of the system, it is positive, and W3 is into the system, that is negative. So cyclic integral of Q means summation of these including sign convention. This should be same for a cycle. That is what first law of thermodynamics for a cyclic process states. Cyclic integral of Q equal to cyclic integral of W. Or you can see like this. I have already told you that whenever, say suppose heat is supplied to the system. So here heat, some part will be converted to internal energy or change in internal energy, and some part will be converted to work. So this for 1 to 2 process, again 2 to 3 and 3 to 4. Here we are saying that initial and final, after third process it should come to the initial state. That means delta U should be 0 after completion of this cycle. So that is why heat and work should be equal. Summation of Q and W will be equal by following the sign conventions like this. This is how a first law is applied to a cyclic process. Cyclic integral of Q equal to cyclic integral of W, or cyclic integral dQ dW. Okay, dW means change or part of work. This is how it is applied to a closed system undergoing a cyclic process. This is a closed system. There is no change in mass of the system. In the next class, we will see how it is applied to a closed system and open system when it is undergoing a single process. Okay. So here we will discuss about non-flow process, that means single process for a closed system, and also steady flow energy equation, which is one form of first law of thermodynamics to a open system, and the applications of SFE. So first we'll see closed system. So closed system is, we know that there will be no mass flow rate, only energy will be transferring in and out of the boundary. Say there is a piston and cylinder. Here initially it is the internal energy of the system is say U1. So during a process, say 1 to 2, you are supplying heat to the system. So what happens if you supply heat? This heat will try to increase the internal energy of the system. U increases, and also due to this increased pressure, there will be some work output of the system. And after this process is completed, here the system will have an internal energy of U2. So here only one process, and that too non-flow, there is no mass transfer. Okay, process. If this happens, what will happen to the energy conservation principle? That is first law of thermodynamics. So initially U1 and plus heat is supplied. Okay, this will become U2 plus W. This is initial internal energy. This is initial internal energy. This is finally internal energy. This is the heat supplied, so that I am taking it is positive. This is heat is work done by the system. So this is also positive. So from this you can say Q is equal to U2 minus U1 plus W, or this can be written as Q1 to 2. That means this is state 1, this is state 2. During intermediate process this happened. What happened? It is supplied, internal energy increased and work is produced. So Q1 to 2 is equal to delta U, that is U2 minus U1 plus W1 to 2. This is known as NFE, which means non-flow energy equation. This is applied to a closed system undergoing a single process. Okay. Previous two cases are only for closed system. Now we will see what will happen if we applied first law of thermodynamics to a open system. So in a open system, mass also crosses the boundary, right? That is by definition, mass also crosses the boundary. Say if there is a system like this. So in a open system it is called as control volume because there are openings in the system. So this is the system and this is the boundary. Here the boundary will be imaginary for a open system. Physical boundary will not be there, only imaginary. So here mass is entering and here mass is leaving the system. Say there can be two types. If mass flow rate, that means mass per second, is constant, then it is called as steady state. Steady state means whatever the mass is entering the system has to leave the system. There is no mass accumulation. That is here m1 dot. A mass is denoted with m and mass flow rate is denoted with m dot. M dot 1 is equal to m dot 2. Input is equal to output. Then it is called as steady flow. There is no change in mass flow rate. If it is not constant, then it is called unsteady flow. That we are not discussing here. Only we are discussing about when the mass flow rate is constant, that is steady flow. So here we'll take it as here also m dot, here also m dot. Okay. Here pressure is P1, velocity, here capital V is velocity, small v is specific volume, and internal energy, specific internal energy U1. So there may be a chance that inlet is at higher position than outlet. So this is inlet 1, this is outlet 2. So this is at a higher position and this is at a lower position. So if it is at a higher position and here it is at a lower position, there is a chance of potential energy difference. So we have to consider internal energy. So we are saying if we apply first law of thermodynamics to an open system, whatever energy going in should be equal to energy coming out. So here there can be energies involved is, we'll see what are the energies involved here. So it is having some internal energy. So internal energy is there. It is due to mainly temperature. If it is having pressure and volume, then flow energy will be there. If it is having Z1, then potential energy will be there. And also we are saying that mass is entering the system with a velocity. So there will be kinetic energy. So during this process, we will say that we will supply some heat. So Q is going in and there is some work extraction. So heat is going in and work is coming out of the system. So we will equate energy going in and energy coming out of the system. So energy is coming in, will have internal energy which is U1, flow energy which is product of pressure and velocity. Here we are taking specific volume. Here P1 is, so m dot is mass flow rate. P1 is, sorry, here P2, this is pressure. Capital V2 is velocity. Small v2 is specific volume. So specific volume is volume per kg, kg per second. Units for mass flow rate is mass per second. Pressure is pascals, which is Newton per meter square. Velocity is meter per second. Specific volume is meter cube per kg. And also U2, which is internal energy. Here small means specific internal energy, that is energy, internal energy per mass, joule per kg. So internal energy is U1 at the inlet, specific internal energy, flow energy is P into V, specific volume, plus potential energy formula is mgh. So if you take out m dot z into z1 into g, p1 v1 plus z1g, plus kinetic energy is mv square by 2, take m out, v square by 2. So this is the, if you multiply it with mass, it will become total internal energy, total flow energy, total flow energy, total internal energy, total potential energy, and total kinetic energy. All 4 energies came into this expression. And also plus here Q is also going in. If it is applied to the system, it is positive. So Q. So this is equal to, now we will see whatever coming out of the system. So here also mass flow rate is same. U2 is coming out, P2, V2 plus Z2G plus V2 square by 2G plus double. Okay. So from this we know that U plus PV is enthalpy. So if you rewrite this equation in terms of enthalpy, it will become m dot into h1 plus z1g plus v1 square by 2g plus q, that is equal to m dot into z2g V2 square by 2G into plus double. This is known as, here the flow is steady flow, so this is known as steady flow energy equation, or simply SFE. Okay. So now we will discuss what are the applications of steady flow energy equation. So we will apply to different appliances used for heat and work conversions. Okay. So now we will see applications. So now we will discuss about boiler. So boiler, as the name indicates, it just boils the water. And by supplying heat. So water will be coming into the system with m dot and the initial enthalpy, say H1. So there is no kinetic energy and no potential energy, because there won't be any much high difference between inlet and outlet. So water comes into the boiler, we will supply heat to the water, and it gets converted into steam, and steam will go out. Same flow rate will be there for both water and steam, and the enthalpy will increase due to increase in temperature. So if I apply this steady flow energy equation to this, here there won't be any velocity at inlet and outlet, and also there is nothing much difference between Z2 and Z. So steady flow energy equation is m dot into H1 plus Z1G plus V1 square by 2G plus Q is equal to m dot into So here there is no kinetic energy, so this and this becomes 0, and also there is no potential energy difference. So finally we will get m dot into H1 plus Q is equal to, there is no work also, we won't get any work from a boiler. This is also m dot into H2. So from this Q is equal to m dot into H2 minus H1. So whatever the heat supplied to the boiler, it will help in increasing the enthalpy of the water or steam. If you apply the steady flow energy equation, we will get the formula for heat supplied to a boiler. This is the application of boiler. Say if we apply this same steady flow energy equation to a nozzle. So a nozzle is a device which converts pressure energy into kinetic energy. There won't be any heat transfer because this nozzle is insulated. Also there won't be any work output from the nozzle. So here steam enters to the nozzle, steam leaves the initial enthalpy is H1, velocity is V1, enthalpy is H2, V2. We are not discussing about pressure and volume because in H there is internal energy, pressure and volume. H is equal to U plus PV. That is why we are talking about H only. So since it is insulated, there won't be any heat transfer and also there won't be any work transfer. Okay. So first write the steady flow energy equation plus W is equal to plus this is 0, this is also 0. So here the height is also same, so Z1 is equal to Z2, this will also cancel out. So here m dot can also be after some time. So finally m dot into h1 plus v1 square by 2g is equal to m dot into h2 plus v2 square by 2g. Here mass flow rate is also same. So finally what will happen is v2 square by 2g minus v1 square by 2g is equal to here actually the formula for kinetic energy is half me square. There won't be any g in this, and also here also there won't be any g in the velocity part, only half me square. So only v1 square by 2, v1, v2 square by 2. Here also there won't be any g. I'm sorry for that. So v2 square by 2, if this goes this side, this goes this side, v2 square by 2 minus v1 square by 2 is equal to h2 minus h1. So generally at the entrance of the nozzle velocity will be very less. So if you neglect this, will become v2 square by 2 is equal to h2 minus h1, or v2 is equal to square root of 2 into h2 minus h1. So keep in mind that this h should be submitted in joule per kg. So generally enthalpy will be given in kilojoule per kg. So what we will do is we will multiply with 1000, so that now we can submit h2 in kilojoule, h2 or h1 in kilojoule per kg. That is why this 1000 comes extra. This is the formula for velocity at the exit of a nozzle. This is one application where we will apply just first law of thermodynamics to determine the velocity of steam at the exit of a nozzle. Okay. Next application is turbine. So turbine is a device which converts thermal energy into, say this is a turbine. This what will this turbine will do? There will be steam entering into the system, and steam leaving the system. It will have some enthalpy, and there is no heat transfer. This is also insulated, and turbine gives work out of the system. So if you apply the here there won't be much difference between potential heads at the entrance and the exit. So here what will happen is, if we apply the steady flow energy equation plus W is equal plus Q, it is input to the system, so plus Q equal to m dot into H2 plus Z2G plus V2 square by 2 plus W. Okay, so here Q is 0 and also velocities can be neglected. Z1 and Z2 are equal. So we will get m dot into H1 is equal to m dot into H2 plus W. So W is equal to m dot into H2 minus H1 minus H2. This is the, if you know the enthalpies of steam at inlet and exit, we can easily calculate the amount of work produced by a turbine. This is how first law or steady flow energy equation is applied to a turbine. Another important part in a steam power plant is condenser. So condenser, as the name indicates, it helps in condensing the steam into water. This water is called condensate. Means, say this is a heat exchanger where steam will be coming into the condenser and water will be going out of the system. Whatever the mass flow rate entering into the condenser will leave the condenser. So here enthalpy is H1 very used. So here heat is rejected out of the system, so Q will be minus and there won't be any work output from the system. So if you apply the steady flow energy equation, H2 plus V2 square by 2 plus Z2G plus W. Here Q is negative because heat is rejected by the system. So this will be minus Q and there is no work. There won't be any difference between potential energies and kinetic energies. Only there will be difference in internal energy and pressure and volume. So m dot into H1 minus Q is equal to m dot into H2, or minus Q is equal to H2 minus H1. Minus sign indicates heat is rejected by the system. Okay, this is how steady flow energy equation is applied to a condenser. In the next class, we'll see how to apply this steady flow energy equation for solving the problems, and we'll discuss about applications and limitations in the next class of the thermodynamics.